If I were to ask you, how do you test this fuel pump? What would you tell me? Would you say, check power and ground at the fuel pump connector? Or would you say, remove the relay and bypass the relay to see if the pump comes on? Or would you say, break out the scope and do a current ramp? Well, if you did any of the above, you're well on your way to replacing a fuel pump that likely isn't bad. Learn what I mean in today's Service Done Right. Today's episode of Service Done Right is brought to you by Delphi. Be sure that you visit their website at www.delphiaftermarket.com. You've determined that the cause of your customer's drivability concern is a result of low or no fuel pressure. And if you use any of the methods that I mentioned earlier to test a brush-type pump, then you would very quickly determine the cause and needed correction for that concern. However, if you tried it on this pump design, you're going to find yourself going down the rabbit hole and replacing a pump that didn't need to be replaced. Why? That's because this is a DC brushless motor and it works completely different. But before we get into the details of how this works and how to test it, let's review how a conventional brush type pump operates. There are numerous components inside the pump housing, including the permanent magnets attached to the inner case and a rotor comprised of coils of wire, typically 8, that terminate at commutator strips located at the top. 2 carbon brushes, one supplying system voltage and the other ground, are in contact with the commutators 180 degrees apart. These commutator strips are the 2 ends of one of the individual coils. When the circuit is closed, current flows through the winding connected to the brushes and a magnetic field develops. The poles of this field are in opposition to the poles of the permanent magnets, and the two try to push away from one another. This begins the rotation of the rotor. Of course, as the armature rotates, it quickly breaks the connection for that particular winding, but it's almost immediately replaced with another winding's connections. And this helps to ensure that the magnetic field strength remains relatively stable. A brushless DC motor, in its simplest terms, is a brushed motor built inside out. The permanent magnet parts of the motor are located on the armature, and the windings are now attached to the outer case. In the case of the 8 windings that we saw on the brush type motor's armature, this stator only has 3 coils, connected in either a Y or delta winding, similar to an alternator stator. In addition, the wear items, the commutator strips, and the brushes are gone. A dedicated fuel pump control module pulses voltage through the 3 stator windings in sequence, 120 degrees of rotation apart. The end result is the same. The rapid buildup and collapse of the magnetic field in the 3 stator windings creates that opposition to the permanent magnets on the rotor to get the rotor to start turning. What do you say we take a look at what the test results might look like on a DVOM and a scope when looking at a brushless DC motor? So let's start by looking at the schematic. Now I'm sure that you've seen 4-wire connectors at a fuel pump before, so that alone is not going to tell you whether it's a brush type or brushless. However, on this one there is a clue. If you look at the first 3, the black, green, and blue wires, they're labeled W, V, and U. And if you're familiar with hybrids, that's the same way we distinguish between the 3 phases of a motor generator. So that's a clue. Now what do you say we hook up a DVOM to one of the wires and see what kind of reading we get? All right, I've got the meter connected. So now I'm just going to turn the key to the on position, or in this case it's a smart key, so we're just going to hit the start-stop button. To the on position. And we have a reading of 12.8 volts. So we got a fully charged battery, number one, we know that. And that, if we were looking at either a brush type or brushless pump, big difference though. If we had a no start condition related to fuel, and you were checking a brush type pump, you may look at the connector wiring and say, okay, well, I've got voltage to it, so that's not the problem. But in the case of a brushless pump, that's not a good reading. There is no signal being sent to that pump. So the brushless pump may not be functioning at all. Let's see what happens when we start it up. You can see the voltage is now dropped to 6.9 volts. If this was a measurement that you took on a brush type pump, that would be indicative of a problem, wouldn't it? And you would probably raise your eyebrows at that and go looking for a cause of voltage drop. However, on a brushless pump, this is a normal reading for a pump that's running. How are we going to know for sure? Time to break out the scope and see the differences in the patterns. So now I have the probes for the scope attached to the fuel pump. I have a probe going into the UV and W wires, and I also have an amp clamp around one of those wires. Try to look at it with the ground. Nothing coming across the ground that's usable. So if you were to try to do a current ramp on the ground wire and you saw that, you would suspect the pump is faulty. I want to show you that's not the case because we're looking at, again, at a brushless pump, and there is a huge difference. So I always like to share how I set the scope up to get my first capture. It always has served me well for 95% of the scope captures I want to get. At least it gives me a starting point. And what I mean by that is we're going to start with what's called the 20-20 rule. And what that means is I'm going to set all my channels that have the UVW leads attached to 20 volts for the sweep. And this will cover just about everything on a 12-volt system, right? So that's the first 20 of the 20-20 rule. I'll leave the amp clamp where it is for now. And time is the other. It's 20 milliseconds per division. That's about the amount of time it takes, or the 200 milliseconds across the screen is about the time it takes for a 720-degree rotation of the engine at idle. So I'll get something on the screen. It may not be perfect, but it gives me a place to start. So with that being said, let me start the engine, and we'll see what it looks like. So I've got a pattern on the screen, but it's pretty much useless the way it is. We need to kind of fine-tune that a little bit. So let's start by increasing the voltage. That will cause the pattern to shrink down a little bit. And we'll change that on all three of the UVW channels. And now I have something I can manipulate a little bit. So let's just kind of separate it. And we'll bring one up. We'll bring one down. And then the only one I have left is the current. We'll bring that down below. Okay, now you see something interesting already on the current pattern. Notice how the current pattern is going positive and negative. That's an important distinction I want you to keep in mind as we proceed. Still a little wide, a little hard to see, so we're going to do that, change that by adjusting the time base. If I lower the time base, I make it faster, I can spread that out a little bit. Let's go down to 1 millisecond. Probably a little too much there. 2 milliseconds. That looks pretty good. And we're going to go ahead and stop it right there so we can take a look at it. So here's what you see here. You've got the UVW feeds to the fuel pump. And again, this is a stator, a 3-winding stator, and it's on the outer circumference of the case. And then, of course, there's a permanent magnet rotor. So how are we going to get that rotor to turn? Well, the permanent magnet has north and south poles, correct? So I need to make a north pole, a south pole, a north pole, a south pole, in order to turn that pump through that 180 degrees of rotation. Now, if I had enough momentum, that's all I would need, but I don't. So I have 2 more windings in 120 degrees opposition to one another in order to keep that rotor moving. But what I want to stress again is positive, negative, positive, negative. How do we know that? Look at the current pattern. Negative, positive, negative, positive. So we're changing the polarity through the winding. For U, then V, and then W. Changing the polarity changes the poles. Let's just say north-south, south-north, north-south, south-north. And that is what's keeping that in opposition to the permanent magnet poles and keeps the fuel pump spinning. If you were to look at this and there was a problem with one of the windings, then you would see a problem in the amplitude change. If there was a short in the winding, for example, the amplitude would be lower on the affected winding, and you would be able to see that here on your scope capture. If it was a problem with no signals being seen at all at the fuel pump, Well, then I would be going to the fuel pump control module. Is it getting the information it needs? Is it sending the signal out? Is it some break in the wiring between the two? Or is it the fuel pump control module itself? These are just a few things you want to keep in mind when you're troubleshooting a brushless type fuel pump, and then completely different from a brush type pump. Don't let those initial readings throw you. Make sure you look at the schematic and identify exactly what kind of pump that you're working on. Here's another example of the brushless fuel pump waveform taken at the fuel pump control module. Remember, where you take the capture, what type of scope you're using, and whether or not you use a low-pass filter can affect the pattern you see on the screen. And while this one looks much different, you can still see the 120-degree phasing of the UVW windings and the current polarity changing. And just like the one I showed you earlier, if a stator winding has a problem, you'll see it here. Now, if you do determine that the fuel pump needs to be replaced, make sure that you perform a critical but often overlooked step, and that's to clean the tank before you install the new pump. Any debris that you leave in the tank could lead to the early demise of that brand new pump, no matter who the manufacturer might be. And Delphi has actually come out with this really cool little cleaning wand to help you make sure you can clean the tank thoroughly with a minimal amount of trouble. In fact, I will leave the link to the wand in the video description so that you can get a few for your shop. Like I said, it makes it very easy. You can replace the ends, and then you can get in with your cleaning mixture and get way down inside the tank with no problem and get everything scrubbed nice and clean before you put that new pump in. Again, don't overlook this critical step if you want the job to be a service done right. And when you're considering a replacement pump, choose a Delphi pump. After all, they are a Tier 1 manufacturer and they supply parts to the OEMs as original equipment. So why not choose the same for your customer's aftermarket replacement? If you'd like more information about the line of Delphi products, be sure to visit their website at www.delphiaftermarket.com. Well, that'll do it for this edition of Service Done Right. Thanks for watching.